Okay, so welcome. So let us have a few examples on dead load and live load. So let us consider this problem. So this problem came from the book of Hibbeler. So the floor of a heavy storage warehouse building is made of 6 inches thick stone concrete. If the floor is a slab having a length of 15 feet and width of 10 feet, determine the resultant force caused by the dead load and the live load. So basically, the slab is designed by its tributary area, which is 15 by 10. So let us take note of that. So the tributary area of the flooring is 15 feet by 10 feet. So of course this is equal to 150 feet squared. Okay, so for the dead load, let's consider the dead load now. We consider the permanent items. What is the permanent items? This one, 6 inches thick stone concrete. So we're going to search that into the dead load tables. So on the dead load tables, we can see here on table 1-3, we're going to search on 6 inches thick stone concrete. So where's that? Stone concrete. We have here stone concrete per inch millimeters, or per inch or per millimeter, because our unit here is in terms of pressure, PSF in English, and kilonewton per square meter in SI. So we're going to adopt this one. This is adopted. We are in English system of units, so we're gonna pick this one, 12. Okay, so 12 PSF per inch. So that is 12 PSF per inch. So for stone, we have 12 pounds per feet per inches. By the way, this is square feet per inches. Okay, so how shall we come up with the unit force? Because we are to determine resultant force. So the force is pounds in English actually. So what we do, if we are going to multiply 150, we are going to eliminate now the feet squared here, and then we have an inches that remains to be at the denominator. Of course, inches here refers to the thickness, and it's already specified in the problem that is 6 inches thick. So basically, this will just be multiplied by 150 square foot. This is cancelled. Okay, and the 6 inches thickness, which also eventually be cancelled. So therefore, the dead load is obtained. Okay, dead load now here is obtained. So 12 times 150 times 6, that is equivalent to 10,800 pounds. So this is our dead load. So next is, what is the corresponding live load? Because one of which we need to obtain is the live load here. Basically, we are to look what will be the occupancy of the floor. So the floor is a heavy storage warehouse building, heavy storage warehouse building. So where shall we get that one? Heavy storage. On table 1-4. So on table 1-4, where's that? Heavy storage warehouse came to be 250 PSF. Okay, so this is 250 PSF. We're gonna pick that one. So therefore, we have live load is equal to 250 pounds per square foot. Of course, basic, just multiply it by the area for this to be cancelled. So therefore, live load is equal to 250 by 150, that is 37,500 pounds. So for the total resultant force, or the floor load is equal to dead load plus live load. That is 10,800 plus 37,500. We have a total floor load equal to 48,300 pounds. Okay, so this is for the first additional problems. Okay, so similarly for problem number 2, the floor of the office building is made of 4 inches thick lightweight concrete. If the office floor is a slab having a length of 20 by 15 feet, determine the resultant force caused by the dead load and the live load. Just the same, we start with computing the tributary area of that floor, that is 20 by 15, and that is equal to 300 square foot. Okay, so first proceed to the dead load. What are the items for the dead load? The 4 inches thick lightweight concrete, that is a flooring. Okay, the self weight of the flooring with 4 inches lightweight concrete. So where's that? Where's the lightweight concrete? Here, if we have table 1-3, actually we have here the value. So we're going to adapt this one. Lightweight concrete per inches is 8 PSF, or 8 PSF per inches. So we have 8 pounds per square foot per inches. Alright, so now again we multiply that by 300, or the tributary area, as well as the thickness, which is 4 inches, so that this denominator is eliminated. So we have dead load equivalent to 8 by 300 by 4. We have 9,600 pounds for our dead load. Next, for our live load, say live load is equal to, we need to determine what is the usage, the function of the building. So according to the problem, we have office floor. So it's obvious that we have office floor. Again, we refer to the table of the live load, where is the office floor here. We have offices. Okay, so we're going to adapt here in terms of English because we are in English system of units. So 50, that is 50 PSF or pounds per square foot. Okay, we have 300 feet squared as the tributary area for the floor, so that it will just be cancelled. So this is how much? L is equal to, we have 15,000 pounds. Okay, so as a total, we have total floor load is the sum of these two, dead load plus live load. So we're going to directly compute it now. We have 9,600 plus 15,000, that is 24,600 pounds. So this is the answer for number 2. Okay, for the third problem, we have here a cross-section of a T-beam reinforced by this reinforcement. The dimensions are given, the thickness. We have here actually the flange, and this stem is the web of the T-beam here. So it has already the gamma, given gamma. We are to determine the dead load per foot length of the beam. Per foot length, so meaning it refers to W. Remember W? W is actually pounds per foot, meaning this pounds is distributed all over a foot according to the problem. So what we do is to capitalize on that gamma. So I'll just write the given 150 pounds per cubic foot. Okay. Again, how shall we arrive at the weight? We have said that the weight is simply gamma times volume. Again, if you cannot manage to memorize this, just refer to the unit. Basta alam nyo na yung pounds is a unit force. So meaning, to eliminate this, or to come up with the pound, we eliminate the foot cube at the denominator by multiplying it by the volume. So simply, weight is equal to gamma volume. And then, after which, we divide the weight by 1 foot to come up with the pounds per foot unit. So in this case, we'll just have to determine the area first, because per foot of length we'll just have this one. Okay, so we're going to have a 1 foot strip out of this cross-sectional area, and then compute for the area. Of course, it's advisable that we just divide this by 2 rectangles, say rectangle 1, rectangle 2. So that is one solution. Or if you opt to have what? The larger triangle or rectangle, I should say. We consider a large triangle there. Okay. Straight edge. I'll just have to draw a large rectangle. Bubuin mo yan, and then just deduct this portion. We just deduct this portion, right? We just deduct this 2 rectangles in it as an option to come up with the area of the T-beam. Okay, so it is up to you what is your convenience. You can do a composite area composing of two rectangles, dividing it by the web as well as the flange, or buuin nyo yung rectangle and then just deduct two smaller rectangles. Okay, so is that clear? Now let us have the dimension of this hollow or this space here. We need to deduct this rectangle. Of course, we need to have the dimension of that one. So if this is 40 minus 10, that is 30, that is to be divided by 2. 40 minus 10 is 30 divided by 2, that is 15. We have 15 inches here and also 15 on the other side. So 26 minus 8 is 18 inches. So as simple as that. Let us now proceed to solve the cross-sectional area. Okay, the cross-sectional area of our beam here. We said that is equivalent to the area of the bigger one minus 2 area of the smaller one. Okay, so the area of the bigger one is 40 by 26. Okay, minus 2 times the dimension 15 by 18. So therefore the area is equal to 500. We have 500 what? What is the unit? 500 square inches. Okay, so 500 square inches. We proceed to this one, to this formula. Okay, we have, what is the gamma? 100. Say W is equal to 150 pounds per cubic foot. So we're going to multiply that by what? 1 foot, of course, because we are concerned per foot of length. So we're going to have here 1 foot. One of the foot here is eliminated. We still have square foot. However, the derived area here is in terms of inches. Of course, we still opt to place that one, 500 inches squared. To be consistent in the units, we convert this into foot, square foot. Okay, what is the factor or the conversion factor in 12 inches? Of course, we know that in 12 inches there is 1 foot, and all of this should be squared, so that this is squared, that is squared. Okay, this is squared, that is squared. Okay, so that what? Feet squared times feet, that is feet cube is cancelled. So the resulting unit is pounds. Okay, so the resulting unit here is pounds. So finally we have a value of W equivalent to 520.83 pounds. So we just divide it by 1 foot, because per foot of length, according to the problem, just the same, we will be having the same value but a unit which is 500 pounds per foot. Okay, so that's it for the third problem. Okay, so next problem, problem number 4. The New Jersey barrier is commonly used during highway construction. Determine its weight per foot of length if it is made of plain stone concrete. So it is just a matter of determining the volume, of course, and then multiplied by the unit weight that is found on the table of the dead load. And obviously it is found in table 1-2. Minimum densities for design loads for materials. We have that to be stone or concrete, plain stone. Okay, so concrete plain stone, we have 144 PCF, 144 PCF, or the density or gamma is equal to 144 PCF. What is PCF? Pounds per cubic foot. So again, it is just a matter of getting the volume, because as we are familiar now, by this time, the weight is just equal to the gamma times volume. Okay, so let us practice geometry. So we illustrate again this section here. Perhaps we have the cross section here. Okay, the top, this is the sides, another side, another vertical. Okay, this is a symmetrical one. Okay, we have this to be the other side. Okay, so at least we have this asymmetrical one. Okay, so this is assumed to be symmetrical. Okay, so the bottom dimension here is 24. Of course, we can actually convert this into composite areas. See, I'll just have straight edges here. First, let us have here a rectangular area. Okay, and a triangular area here. Okay, we have another triangular area there, and a rectangular area again, and a rectangular area. So basically, we will be having how many? So we'll just label those. Say number 1, sorry, area 1, area 2, area 3, and this is the fourth area. So 1, 2, 3, 4 is multiplied by 2 by symmetry on the right side, and then we are going to add the fifth area, because area 5 is the middle, or a single rectangle here. Okay, so what is the dimension of 1 now? So here's the triangle. Okay, we determine the dimension. Of course, we know the angle. The angle is 75. Okay, what else do we know about that one? Nothing more. 75. Do we know this height? No, we do not know this height. Do we know this base? Not yet, but we can solve. Okay, we can solve that one. Say if we can solve, then we will be having that as x. Unlike on the vertical, we really do not know. We do not have any reference in getting y here. But in the base, we still have to refer to the total distance here and the top distance, 24. So this is 4. Okay, so if that is 4, that is 24. 24, 24. So, let us erase this one, delete this one for a while. So the total here is, okay, total here is 24. So that this is 4. So what is left? 10, 10. Isn't it? So this is basically, this should be equal to 10. Okay. So we have obtained a dimension. And what else do we know? We know this to be equal to 6. And then this one is how much? This is 12 inches. So still have a progress. If we could work with the triangle 3, then we can obtain this base, right? Because we have 12 here, and we also have the angle there. Okay. Okay. So from this, working on the triangle 3, we can now determine this base, right? If we could determine that base, then we can directly determine this by subtracting it to 10. So as we can see here, the solution, we came far too long from triangle 1 in order to get some dimensions here. So what I'm trying to point out is that sa una pa lang, wag nyo nang ipilit kung wala kayong makukuhang dimension. Perhaps on other composite areas, you can find anything useful that is given on the problem. So moving on for the triangle 3, okay, working with the triangle 3, we leave this for a while. For a while, we're going to leave that one. Okay. So at triangle 3, we have this, triangle 3. So this is 55 degrees, and then we have a height of 12 inches. Okay. So if that is 12, what function to be able to get this one? What should be the function? Of course, tangent, because we have opposite, and adjacent. So writing the tangent function, tangent 55 is equivalent to 12 all over, perhaps we can label this as z. Okay, 12 all over z. So therefore, z is equal to 12 all over tangent of 55. So we have 8.4 inches. So if this is 8.4 now, okay, so we're gonna place that there, 8.4. What is the remaining if this is 10? What is this dimension? So 10 minus 8.4 is 1.6. So basically this is 1.6. Okay. and this is 1.6 as well. Okay, that is what we are looking for. X is equal to 1.6 here. This is what we are looking for a while ago. Okay, so again, by tangent function we can get this dimension. Say I'm gonna label this as y. Okay, by tangent function, tangent 75 degrees, opposite to that one is y all over 1.6. So therefore, y is equal to 1.6 tangent of 75 degrees. We have y is equal to 5.97. 5.97 inches. So I'll just place that one, 5.97 inches. Okay. Do we have a complete dimension now? Of course, we have. Then, we will now proceed to the calculation of the area. Okay. For the calculation of the area is equal to what? 2 y2, because we're going to multiply those four areas. Area 1 plus area 2 plus area 3 plus the fourth area. So these are the area to be twice or to be doubled because of the other side, and then a single area 5. Okay, so moving on, let us compute now the area, individual area. Area 1, we have a triangle. We have 1/2 base times height. Base is how much? 1.6 by 5.97. And then area 2 is a rectangle equivalent to 1.6 by 12. Okay, and then area 3 is another triangle. We have 1/2 8.4 by 12, and then area 4 is another rectangle equivalent to what is that? 6 by 10. 6 by 10. Okay, 6 by 10. We close it and then add the fifth area. The fifth area, as we can see, that is 4 by the total height. Okay, so what is the total height here? What is this? Total height from top to bottom is, we have 5.97 plus 12 plus 6. 5.97, here it is, plus 12, here it is, plus 6. So we add those one, we have 23.97. 23.97. So that should be added here as area 5. So we have 4 as the base times the height of 23.97. So finally, we have the area. So perhaps you can calculate that one. We have 364 1,144.63 square inches. Okay, so we obtained now our area. So we review now our unknown, determine its weight per foot of length if it is made from plain stone concrete, and we identified the gamma of that one, 144 pounds per cubic foot. Okay, so therefore weight is gamma times volume, so that gamma here is 144 pounds per cubic foot, and then volume is area times area times length, and length is set to be 1 foot strip. Okay, so we'll just have to place that one for a while. The area in terms of square inches, we have here 364 inches squared. Okay, let us have a conversion factor again. In 12 inches there is 1 foot, and again all of these are squared so that we can cancel that one, and then again this is multiplied by a foot strip. So basically all of those now are cancelled. So 144 all over 12 squared. 12 squared is actually 144 also. Can cancel that one. So what is left is 364. 364 pounds. So if we wanted to per foot, just divide it by a 1 foot. So we come up with 364 pounds per foot. Okay, that's it for this problem. By the way, this is 364.63 to be complete in within 2 decimal places. 364.63. Okay, pounds per foot. So this is the weight of that barrier in terms of pounds per foot. Okay, so that's it for this problem.